Hello, everyone. Thank you for joining and welcome to Accelerating Big Data Analytics Applications with FPGAs and OpenCAPI. My name is Peter Hofstee. I work at IBM in Austin, Texas, and part-time at Delft Technical University in the Netherlands.
In this module, we'll take a look at some examples of using CAPI interfaces for accelerators. We'll look at three examples: Gzip implemented on a CAPI accelerator, a Capi Flash, so non-volatile memory implemented on a CAPI interface, and finally text analytics acceleration with a CAPI-based accelerator. So the first example is the IBM Gzip FPGA accelerator. I'm not going to describe here in much detail how the FPGA Gzip kernel works. But let me list some of the attributes of this accelerator. It obviously saves storage and I/O bandwidth, and because of the absence of device drivers, there's a lot less CPU overhead. Very little software load. And it frees up the CPU cores, compared to handling the function in software or working with I/O-based drivers. FPGAs generally have a power efficiency benefit, and the same is true here. It supports the standard Gzip format. And pretty good compression, decompression rate. Remember, this was back in the CAPI 1.0 days. And I'll show you some of the achieved speedups. Generally, on compression, it could go all the way up to 30x, and on decompression, it was more like 4x speedup. And this is relative to a single-threaded CPU implementation. The compression ratio, is a bit lower than, say, a Gzip -9 kind of option, but it was quite good. Certainly, substantially better compression ratio than byte-oriented compression algorithms like Snappy. So if you look at the second and third entries here in the box, you see that with the accelerated compression, the time taken is about 1.5 seconds with very, very little user time and a very modest amount of system time as well. Whereas in the accelerated case, the non-accelerated case, it takes more than an order of magnitude longer. And of course, that time is largely in user space. Another example here is secure copy protocol, which happens to use libc under the covers. And you see that by leveraging the accelerator, the bandwidth increases almost fourfold. Gzip compression is actually fairly, you can find it in lots of places. For example, PDF files are often Gzip compressed. Indeed, by leveraging the CAPI protocol, the Gzip accelerator was able to improve real applications, due to a lower latency to invoke the accelerator, and of course the higher bandwidth, and less load on the host CPUs. The accelerator actually has since been integrated on Power and IBM C-series processors.
Our next example of the use of a Capi-based interface is Capi Flash, also known as the IBM data engine for NoSQL. This slide shows what the application stack for Capi Flash looks like. In this particular case, with a big Redis key value store on top. So the flash array, either in the form of a separate storage array or in the form of flash stick devices attached on the accelerator card, talks to the Capi attached functional unit, which is connected to the host processor via the processor service layer that implements the Capi interface. A block library allows user space transfers from the storage device to host memory. We could have implemented, byte level load stores as well, but because of the characteristics of Flash in this particular case, a user space block transfer was more efficient. There is also a key value store library on top of that. And then that library is leveraged by the Redis implementation that presents key value store to the clients.
By now, the benefits of a Capi-based interface, probably familiar to you. Because you don't have to go through a typical IO-based stack, the number of instructions per operations is vastly reduced. In this case, from 20,000 or more to the 4,000. And by the way, because the operating system is not involved in the Capi way of operating things, it's not only the case that your average latency improves, because there is no OS jitter involved, your worst case latency also vastly improves. And the end result is that you're saving a lot of CPU cycles by using an interface like this, and also are able to achieve these block copy operations and ultimately the key value store operations at very high performance. And while of course comparisons to file system based I/O are most dramatic, even more direct means of accessing Flash like NVMe can still be outperformed by a Capi based interface. So in these graphs here, you see that a Capi interface into NVMe can yield benefits both in terms of the number of instructions, CPU instructions that are executed per IOP, as well as the number of IOPS per CPU thread that can be supported.
Our final example, and one of my personal favorites, as it is one of the earliest uses of Capi type interface, and one that really benefits from the shared coherent memory, is text analytics acceleration. So in this case, a Capi-based accelerator is used to accelerate queries in a language called AQL, a part of the then IBM System T text analytics offering. These queries contain expressions operators that like regular expressions or dictionary matches or join operations, etc. That can be very productively accelerated on the FPGA. But, you know, an FPGA has resource limitations. FPGAs are not infinite in size, and, you know, that goes both for the logic as well as the embedded memory. And also, not every function, not every operator that occurs in the AQL expressions may have been implemented on the FPGA. However, because the FPGA shares a virtual address space with the host, invoking the accelerator for a part of a regular expression becomes for a part of the AQL operator tree becomes very feasible, and that's what was done in this case. This slide gives you an overview of how the System T accelerated solution is constructed. On top, you see the original System T in orange. And you know, during compilation of the AQL language, the operator graph is partitioned into parts that can execute on the CPU and parts that are productive to accelerate on the FPGA. They are then automatically compiled to generate the code for the FPGA, and runtime combines both the software and hardware FPGA-based execution to do the equivalent thing of the original System T evaluation.
Now, System T had a parallel execution environment. So this slide here, you see a bit more detail of the runtime environment for System T. So there were multiple worker threads that might reach a phase where the FPGA would be beneficial in accelerating the function. And there were multiple instances of accelerators on the FPGA. This slide shows we had good opportunity for hardware acceleration. So, you know, the vast majority of the operators, and certainly those that took the most time, were supported on the FPGA. And on this slide, you see that even for documents of really, really small size, there was already a good benefit for for accelerating the software with this AQL accelerator, and you know, a bigger benefit as the size of the documents grew. And this is you know, compared to a parallel implementation of the software. So I think this was a very nice result. In this particular case, it was not productized, but that was not for lack of performance. It was because the emphasis in query acceleration or text analytics, I should say, shifted from these kinds of regular expression-oriented expressions to machine learning and deep learning approaches. So to summarize, in this sub-module, we showed you 3 examples of OpenCAPI accelerators. The first, a decompression example. The second, key value store, where OpenCAPI was used as an efficient interface into flash storage. And finally, text analytics acceleration with an FPGA accelerator for System T, which truly leveraged the shared memory attributes between the host and the FPGA accelerator.